Day by day, as we walk through the streets, follows the flow of our lives, we always encounter the curves. The things that help us move on our day and give spices to our lives. Car wheels, Ferris wheels, balls, Earth's revolution, rainbows, MacDo's logo, and the Twin Arc in Japan. These are just some examples of conic sections. But how? When did it start? And what's the story behind this concept? The knowledge of conic sections can be traced back to ancient Greece. These are among the oldest curves and are the oldest math subjects studied systematically and thoroughly. Menaechmus is credited with the discovery of conic sections around the years 360 to 350 BC. It is reported that he used them in his two solutions to the problem of doubling the cube. It is when King Minos wanted to build a tomb and said that the current dimensions were subpar and the cube should be double the size, but not the length. Many mathematicians of that time tried to determine a solution to the problem, but it wasn't until the idea came to Plato's Academy that it was solved by the mathematician Menaechmus. He discovered the curves parabola, hyperbola, and ellipse. However, he did not use these terms. Instead, he called a parabola a section of a right-angled cone, a hyperbola a section of an obtuse-angled cone, and an ellipse a section of an acute-angled cone. The cone itself was a single napcone in which the plane was perpendicular to the axis of symmetry of the cone. Following the work of Menaechmus, these curves were investigated by Aristeas and of Euclid. The next major contribution to the growth of conic section theory was made by the great Archimedes. Though he obtained many theories concerning the conics, it does not appear that he published any work devoted solely to them. It is said that he described the different sections of the cones with names, and Apollonius just built of that idea from him. Apollonius, on the other hand, is known as a great geometer. On the basis of his text Conic Sections, an 8-book series on the subject. The first 4 books have come down to us in the original ancient Greek, but books 5 to 7 are known only from an Arabic translation, while the 8th book has been lost entirely. Apollonius gave the terms parabola, hyperbola, and ellipse derived from the Greek words for ellipsis, parabole, and hyperbole. He also began to use a double napcone instead of a single napcone because it had a better use of defining the conic sections. After Apollonius was the mathematicians Pappus and Proclus, who are the reasons why previous mathematicians are credited with examining conic sections. They did this by providing many commentaries on their predecessors' work on conics in the 5th century. After these two mathematicians historians, it wasn't until the 15th century, around the era of Renaissance, that there was a revival in the interest of Greek culture and knowledge. With this era came the works of Johann Kepler. In the year 1605, he was the first person to show the elliptic path of Mars revolving around the Sun. This new discovery fueled motivation in the study of conic sections. However, it dealt more with a focus on the mechanics and astronomy. He also claimed that the line and parabola are extreme types of a hyperbola, while the parabola and the circle are extreme types of an ellipse. In addition to these pioneers, there were many other mathematicians that contributed to conics such as Newton, Poncelet, Steiner, Dandelin, Dupin, Jurgen, Brian-Kahn, and Chasles.
Let's see if we can learn a thing or two about conic sections. So to start with, what are they and why are they called conic sections? You might probably knew a few of them already, either the circle, the parabola, or both. The conic sections are the circle, the ellipse, the parabola, and the hyperbola. But why are they called conic sections? Simple, because they are the intersection of a plane and a right cone. Before we go to each conic section, let's define first what a conic section is and what are its parts. When a straight line intersects a vertical line at a fixed point called the vertex and rotates about that fixed point, the surface obtained is called a double right circular cone, which consists of 2 cones that join at the vertex. The line that rotates about the vertex is called the generator, and the line that remains fixed is called the axis. A right circular cone has a circular base, and its axis is always perpendicular line from the center point of the base to the vertex. The perimeter of the base is called the directrix. The lateral surface of a right circular cone is called a nap. A double right circular cone has two naps, the upper nap and the lower nap, making it a double nap cone. For a plane that is not perpendicular to the axis and that intersects only a single nap, the curve produced is either an ellipse or a parabola. The curve produced by a plane intersecting both naps is a hyperbola. Each conic section has a unique or typical equation form. These equations can be rearranged in various ways, and each conic has its own special form that needs to be learned to recognize. Given a general form, conic equation in the form ax squared plus cy squared plus dx plus ey plus f is equals to 0, which is the general equation for all conics, or after rearranging to put the equation in this form, this is the sequence that should be kept in mind.
When a single napped cone is cut with a plane perpendicular to the axis of the cone, the curve formed is called the circle. This intersection is a closed curve, and the intersection is parallel to the plane generating the circle of the cone. A circle is a set of all points that are equally distant from the symmetry center, called the radius, and also a circle is a special type of an ellipse. The equation of a circle comes in two forms. The standard formula:
quantity of x minus h squared plus the quantity of y minus k squared equals to r squared.
The general form of a circle is x squared plus y squared plus dx plus ey plus f equals 0. Here are some examples of a circle. Plotting it on our double napped cone, this is the circle.
When a single napped cone is cut with a slanted plane, a curve formed is called an ellipse. This differs from a circle in that an ellipse does not have a constant radius. It has a radius that changes between an x radius and y radius. However, an ellipse has two focal points, which the sum of the length of both focal points to any given point on the ellipse is always the same. These are the equations of an ellipse. The standard formula of horizontal axis is x minus h squared over a squared plus y minus k squared over b squared equals 1. And for the vertical axis, x minus h squared over b squared plus y minus k squared over a squared is equals to 1. The general formula of an ellipse is ax squared plus cy squared plus dx plus ey plus f equals to 0. Here are examples of an ellipse. Plotting it out on our double napped cone, this is the ellipse.
A parabola is formed by intersecting the plane through the cone and the top of the cone. Parabolas can be the only conic sections that are considered functions because they pass the vertical line test. A parabola is the set of points that are equally distant from a focus point and a directrix. A fixed line. The standard equation depends on the axis of symmetry. These are the equations of a parabola. Standard formula for horizontal axis. Quantity of x minus h squared equals to 4a quantity of y minus k. Standard formula for vertical axis. Quantity of x minus h squared equals to 4p quantity of y minus k. The general formula for parabola is ax squared plus dx plus ey equals to 0. Here are some examples of a parabola. Pointing it out on our double nap cone, here is the parabola.
hyperbola is formed when a plane slices the top and bottom section of the cone. The pair of hyperbolas formed by the intersection of a plane with two equal cones on opposites of the same vertex. It is a curve, specifically a smooth curve that lies in a plane, which can be defined either by its geometric properties or by the kinds of equation for which it is the solution set. These are the equations of a hyperbola. The standard formula of horizontal axis is x minus h squared over a squared minus y minus k squared over b squared equals 1. The standard formula of the vertical axis is y equals k squared over a squared plus x minus h squared over b squared equals 1. Then the general formula of the hyperbola is ax squared minus cy squared plus dx plus ey plus f equals 0. Here are some examples of a hyperbola. Plotting it out, our double napped cone. This is the hyperbola.